Hey everybody, this is Alex Merced with another video on concepts related to the data world. This one's a little bit less particularly related to the data world, more than just understanding the role of Java in the programming world, to understand why it's so prevalent in the data world, why so many data tools are written in Java, why Java has this sort of long-standing hold in a lot of places. It's all context, it's all historical context. So let's just talk about like the history of programming languages a little bit in general. So at the end of the day, computers use your typical sort of processor to process things. Okay, so bottom line is, it's just electricity, right? It's just electricity going through circuitry, and electricity has sort of two, at its most simplest form, has basically two states, on or off. It's either electricity is flowing through, or it is not. So then what happens is that basically that can represent two things, a 0 and a 1. Okay, so bottom line is when you take a think about memory, your memory is just basically a bunch of small little electrical circuits, each representing sort of an on or off state, zeros. So essentially everything has to be represented as zeros and ones. That's referred to as binary. So again, if I were to write like binary, it would be like, like 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, and sort of each of these is what's referred to as one byte. Okay? Cool. Okay, and the problem is programming like this, probably not going to be the most easy thing to do. So oftentimes the processor, so again, here we have the processor. So that's going to be the thing that actually processes those zeros and ones, to make it easier to actually do everything the computer is doing, to actually like come up with instructions that come from that. Okay, they're like, okay, how about we don't do this? The processor will oftentimes have its own sort of built-in language called assembly. So there's different versions of assembly depending on sort of what processing circuitry you're using, or what processor architecture you're using. Okay, so let me just see some, let's go to images.google.com and just see some examples of assembly. Okay, so then assembly code would look like this. A lot better than zeros and ones, right? Okay, essentially what you're doing is you're moving, because again, your memory is essentially just a bunch of little lights that can turn on and off, or like little, and then basically they can be 0 or 1. Okay, all these little spots to store either a 0 or 1. So essentially what you're doing is you're manipulating those zeros and ones to send instructions or represent data, etc. This is what's referred to as sort of why they use base 2 numbering. Okay, so what does that mean? Let's go back for a second. Oops, wrong one. Scalar, that's what I want. Okay, base 2 numbering. So what does that mean? We normally, when it comes to counting numbers, we use base 10. So that means what do I do? When I get to 9 and I'm about to hit the 10th number, that's when we go to the next digit. So that becomes 10. So every time I sort of hit a 10, so again, when I hit like 99 and I'm about to hit my 10th 10, then we move on to the next digit. Okay, so basically the base represents when you go to the next digit. Okay, so essentially, base 2 means every time you hit 2, you go to the next digit. So when I get to 1, and then once I get to 2, well, 2 becomes this. And then this becomes 3. Okay, and then this becomes 4. Actually, not even. This becomes 4. Okay, and so forth and so forth. Okay, because again, there's only two possibilities, 1 and 0. Okay, on or off. So you have to present everything in something that can only use those two possibilities. So then you express all numbers using base 2. So again, that's what you're essentially doing. You're constructing everything from that. And assembly just provides a nice abstraction, which means like a layer of simplification on top of that. But still, this is a little painful. This is not, no one wants to be doing this if they don't have to. Okay, so basically, just going back, we have binary at the bottom. That's the lowest level language. Then you're going to have assembly. But the problem is there's different assemblies depending on which processor you're working with. So, Mac processors are going to have a different assembly language than processors like AMD and Intel processors use for PCs. Okay. So that'd be annoying to have to write assembly several times. So then what happens? You end up with the next layer, which is going to be like C and C++. Where now you're actually starting to have like languages that actually like read like English, where you can actually read the code and kind of understand what it's doing a lot better. But again, these are lower level languages, meaning it's still pretty close to here. Essentially, we're now just basically turning into English the directions you'd be sending over to assembly. So like instead of you having to figure out like how memory is sort of allocated and stuff like that, you you can still just request a chunk of memory, okay? But you're still basically work. Point is being you still have to work with memory. Like you don't have to do the kind of granular work you have to do with assembly, but you're still saying, okay, hey, I need to make a variable. Let me go grab a piece of memory. Okay, I'm done with this piece of memory from the heap. Let me deallocate it. So this is all this work you have to do. And then again, because of that, you can easily make a lot of mistakes where you don't allocate enough memory, or you allocate too much memory, or you go outside the bounds of one variable to another. There's also a whole world of mistakes you can make. Okay, like the coding looks a lot simpler. Like again, if I were to look up here, like C++ code, okay, now we're starting to get to something you could possibly read. Okay, I can kind of see what's kind of going on here. I can be like, okay, we're creating a variable that's a string that represents a person. Well, actually, this is a string. Doo-ba-doo-ba-doo. Okay, and then we're taking that person and we're setting. It looks more like they're setting some sort of like hash map. But point is, you have much more readable code. Okay, but still a lot of work you have to do. So then what happened is there's languages, higher level languages, and these higher level languages come with what's called a garbage collector. So instead of me having to worry about getting a chunk of memory for my variables and remembering when to release that memory, there's this program that's just automatically baked into the running of my code called a garbage collector that handles all that for me. Okay, so this would be like using your Python, your JavaScripts, your Rubies, these languages. But because of that, they're a bit slower. Okay, so that isn't necessarily ideal either. So we want something that is going to prevent me from making mistakes like I am here with C++ and having to deal with that level of complexity, but maybe a little bit faster than this. And this is sort of where Java and C# kind of find their place here. Okay, so essentially what happens here is you end up with these languages that work. How's the best way to put it? When you're using C and C++, which nowadays you do have some more modern alternatives like Rust and Go, which are becoming more and more popular. So a lot of times at the bleeding edge, you're starting to see a lot of people adopt Rust and Go as saying, "Hey, I don't need to use this middle layer anymore." But what happens here is that you would compile directly to like your assembly. So I would compile it. I would take this code, compile it to Mac, compile it to Windows, maybe now compile it to like an ARM chip for like cell phones, but you compile directly to binary or to the assembly for that particular architecture. That's what you're doing here. Now here, oftentimes you're interpreting. So then what happens is that the code is being interpreted on the fly and being turned to binary on the fly. Plus the garbage collection overall, that makes for much slower, because when you compile, you're not compiling when you run the code. Okay, here you're doing both at the same time, which, well, makes things slower. So here the idea is we want the garbage collector, we want the niceties of these higher level languages, but we want to get closer to the speed of this. So the trick was, okay, because we don't have to compile the same thing over and over again. That was the trick with Java. Java did not. The idea was like you don't want to have to compile the code once for Mac and then compile it again for Windows. So the idea was like write once anywhere. So the concept was to compile to an intermediate language. Okay, in the case of Java, that's called Java bytecode. Okay, Java bytecode. Okay, so the Java bytecode would essentially get interpreted in real time. Okay, so essentially what would happen is that I would write Java code, and then you would compile that. So in this case, like you would compile to assembly, you would compile the code, which means, hey, you transfer it, and you don't have to redo it every time you run the code. But instead of converting it to assembly, you would convert it to Java bytecode. Java bytecode is essentially a language that's a lot like assembly, but it's a special version for Java. And Java knows how to map Java bytecode to, let's say, assembly for Mac, assembly for Windows, assembly for other architectures. So that case, you don't have to worry about that, and you don't have to recompile it multiple times. So now then what you would do is you would then run that code, and that code would get run by the Java virtual machine, the JVM. And the JVM would then interpret it. Okay, so essentially here there you are having interpretation of that code, and it would just on the fly turn it to the appropriate assembly so that way the computer can run it. Interpreted. Okay. But again, going from here to here is much faster than interpreting from here to here versus like, a language like Python, JavaScript, Ruby that is pretty much, interpreting straight from that highest level all the way down to assembly. A lot more work than this. Okay, we do half the work up front, and then we allow the other half of the work to happen at runtime. But because we do this, because the code that we run is in Java bytecode, you can run it on any operating system that has a Java virtual machine installed. Because a Java virtual machine will always translate it to what it needs for that particular machine. So this was the whole idea of like write once, run anywhere came. Okay, as long as the computer has a Java virtual machine installed, you could write a Java code compiled to the Java bytecode, okay, essentially any jar file, and it would run on any computer that has a Java virtual machine installed. Okay, so it made code very, very portable, which, back in the 90s when basically you didn't really have that ability to do portable code, you basically had to compile to different architectures, and then you also had other programming languages like Objective-C just for Macs, and then, all these languages that try to like in Visual Basic for like Windows and whatnot, they try to like say, hey, you want to program for our platform, you use our language. They just made it a lot of work to create multi-platform applications. Java came along, and actually is one of the only languages that ever actually spent money on marketing itself. It was like I think $5 million marketing blitz at some point in the 90s. So then it became sort of like huge. It was very widely used, and then it was very for that portability. Okay, and got really adopted by a lot of enterprises. And that's where its sticking power comes from. Because nowadays, basically, most huge enterprises that have applications built, they're oftentimes built in Java. They use Java. So it makes it easier to use it with other applications that use Java because you can share those jars. Okay, so it creates this ecosystem that kind of gives a lot of inertia when you're big companies that can't change very fast. Like you can't just like stop using your applications that are built in Java. So you need other applications to interact with those applications and create this momentum for using like sort of Java going forward. But, Java lacked a lot of niceties up until very recently that a lot of modern programming languages had. So people created other languages that compiled the Java bytecode. Okay, so now there's lots of languages that compile the Java bytecode, such as Scala. Okay, let's just write up a few of these. Scala, Kotlin, Clojure, and Groovy. These are probably like your main candidates. And all these languages now have compilers that allow you to use these other languages that have nicer, much more friendlier syntax in a lot of ways, and be able to compile the Java bytecode. So you still get the same benefit of the performance that Java bytecode can do over just having a purely interpreted language. Still not as fast as, let's say, using C++ or C# or Rust or something like that. And again, caveat, okay, bad code, good code in a slower language can still be a lot faster than bad code in a fast language. So just because a language is theoretically possible to make faster code doesn't mean the code that people actually write is necessarily faster. You still have to write good code. Okay? But these languages can compile and take advantage of this sort of Java, which means they can take advantage of all the existing Java libraries. Okay, so basically they automatically inherit everything that already exists for Java, but they also provide an easier way to write code for future Java bytecode type applications. Okay, so and different people like Kotlin has really been embraced for like doing mobile applications. Scala has been really embraced for like data applications because Apache Spark was written in Scala. Clojure and Groovy have their niches. I'm a little bit less familiar with them. Aside from that, Clojure is like based on Lisp. Okay, lots of parentheses, but that's sort of the story there. Okay, and now even in more recent times, there's another thing called the LLVM. Okay, and with the LLVM, you can compile to binary. Okay, so you can take that Java bytecode if you want to get extra speed, you can send it to this LLVM. I forget exactly what LLVM stands for off the top of my head, but essentially it's another sort of virtual machine environment that also enables compilation to binary, and you can use the Java code. I forget if you're going from Java bytecode to LLVM or does you take your Java code to the LLVM, the specifics, but the idea is like this is another trend that you'll see where a lot of companies will still keep using the languages they're used to, because once you get really good with a programming language, your productivity slows down when you switch. So in that case, you want to use what you know, but still get even further juice out of it. But again, a lot of those old databases, a lot of old enterprise applications that are still very much used were built in Java. So this would create this impetus for everything else to kind of in the future be built with Java. This is why you see so many projects in the data space generally start with like Java-based application code, because you're dealing with because they often interface with other Java-based tooling. So that means you need jars. Jars are the files that have all those Java classes that allow you to share that functionality. So that's the story there. But again, you are starting to see some movement towards things like Rust in particular, in writing like newer databases and newer data tools and newer data libraries. And then oftentimes you'll see like Rust implementations used to accelerate things that then have like a Python library built on top of them. So for example, Polars is a data frame library that I think under the hood, like the actual data structures are built in Rust, but then you have the Polars Python library, and you can interact with those data structures using Python bindings. So again, for that consumer of these data structures, they have a nice, easy to use Python interface, but then they can deal with like a really fast Rust construct under the hood, because again, Rust exists in that same layer as like C and C++. I won't get into what's special about Rust. That's a whole other conversation for another day, but it's a pretty exciting language, in my opinion. I'm a big fan of Rust. But yeah, so hopefully that just puts into context sort of Java's role in a lot of this software, why a lot of it is written in Java, and how Java functions, and why Java has the place that it does. Because a lot of times people are like, why don't we just do everything in Python? Like, certain things are really great in Python. Python's really great for writing, the way we interact with things and writing applications around things. But oftentimes, like, the more lower level pieces do need to be written in languages that are going to be a little bit faster than Python, but then Python can then interact with those things in the same way like Apache Spark has PySpark. Basically you're dealing with a Java application, but you're doing it in Python, or with Polars where you're dealing with like Rust based data structures, but you're doing it in Python. That's the part that needs to be fast has to be done in the language that's fast, and then you can write bindings in a language that allows more people to take advantage of that core. In something like Python, where it's much easier for more people to use to take advantage of those pieces that were built in another language. Because at the end of the day, when all a computer cares at the end of the day is that it's all binary. Okay, everything eventually gets there at some point. Okay, it's not like Python or any language creates something uniquely magical. It's all dealing with sort of the same pieces at the end of the day, the same electricity going through circuit boards. So hopefully that gives you just a little bit more context around sort of like the programming world that powers the tools that you use for data, to be able to use those tools more effectively and understand why they're architected the way they are more effectively. My name is Alex Merced. I'll see y'all later.